then I have the pleasure to announce the last question by Jon McCarty from SRI Park in California, thermodynamic properties of carbon in services.
I want to thank the organizers for inviting me to present a paper in this very well organized and very well completely covering the whole range of Fischer-Tropsch chemistry. This is a very nice symposium. It was also very nice to see so many old friends from the days when Fischer-Tropsch chemistry was quite the rage, not that long ago. And in fact, I go back to the days when we were indeed trying to make gas. And if I can have my slide, one of the sponsors I need to acknowledge for supporting our work on the thermodynamics of carbon formation and the reactivity of carbon states on ruthenium surfaces is the Gas Research Institute. And it's interesting to note that nowadays that whole thing is turned around and we're not interested in making gas anymore, but in fact we're working very hard to find ways to use it and convert it into other forms. I'm going to take a slight moment here to grab the pointer. I'd also like to acknowledge my co-workers. Of course, Dr. Henry Wise was with us at SRI at that time. Nowadays, he's a professor at the Stanford University Department of Materials Science. And some of my other colleagues, Dave Sheridan, who did a lot of the work that I'm going to talk about, or what, to the extent that it is there, is now at Catalytica, and a couple colleagues, Bernie Wood and Gilbert Tong, are working on steam reforming, which is one of the things that I will introduce late in the talk. Our sponsors were the National Science Foundation, DOE, METSI did some support related to steam reforming, and Osaka Gas is supporting our steam reforming work that relates to this topic. Next slide will show you what the major thesis of my talk is, that there in fact are quite a few states of carbon that can be formed on ruthenium surfaces as they can be on almost all other metals. You can't just say that there is one type of carbon or even one type of carbide because there's lots of different degrees of coordination that occur on especially supported metal catalysts. But I'll talk a little bit about what we think is chemisorph carbon, and then discuss the formation of an overlayer, and in fact then I'll talk about the hydrogenation and what we can learn a little bit about that from the temperature program reaction kinds of experiments. I will also mention briefly the CO dissociation, but Alex Bell, I see, and various other people will have plenty of time in the coming days to discuss that in much more detail. The next slide shows our system. I think the reason I'm here, I believe, is to talk about the thermodynamics, and this is the recirculation systems that we use to make some of these studies. It just is a closed recirculating loop. We have a little bellows pump, and we simply inject in as pure a helium stream as we can make some CO and follow the reaction until nothing further happens. We then take a sample to the GC with a methanator and a flame ionization detector. We can look at very low levels of carbon monoxide and carbon dioxide. And because we have a fairly large amount of gas in the system, and in fact put a volume in there, we have to make sure that there is a fairly large amount present. We can accumulate after multiple injections a fairly large amount of carbon on the surface. The next slide shows some of the results. This simply shows the amount of carbon in micromoles absorbed per gram of catalyst on the surface of a dispersed, this is a 1.58% ruthenium on alumina catalyst at roughly 450 or 550 Kelvin, a typical Fischer-Tropsch type of temperature. And this shows how much increase in carbon absorbed we see as we increase the carbon monoxide partial pressure. This is in units of 10 to the minus 4 atmospheres. Well, just from the thermodynamics, you can take the CO2-CO ratio, or actually it's CO squared over CO2, and determine carbon activity as a function of temperature and accumulated amount of carbon. And the next slide shows that. In fact, I have my controls right here, don't I? The next slide shows the result. And we ended up plotting all of the data independent, well, not independent, but we have plotted them just against temperature in this slide. This is the activity of carbon with respect to the standard reference state, which is graphite, as a function of reciprocal temperature for all different types of carbon coverage. The interesting thing is that there isn't a lot of variation that we could find between the amounts of carbon. Now, this number that's printed on the slide, which I'm sure is invisible to the people in the back, represents the fraction of our CO capacity of this catalyst at 300K, the fraction of accumulated carbon, and it ranges from about 0.6 down to 0.05, and still there's a fairly good, probably within our reproducibility, very little change, or not enough change to try to break out, but there is certainly an effect of temperature. Next slide. This shows a plot, the same type of plot, only now we're calling it partial molar free energy with respect to graphite of this surface carbon. This is in kilojoules, so it's really not very far removed from the free energy of carbon as a function of temperature. Now, again, there is a scatter of amounts of carbon present on this surface, which is a little disconcerting in this kind of experiment. If it were truly a classic chemisorb state, you would expect some linearity, at least at low coverage, between the free energy of the carbon and its quantity. But we don't see that kind of large relationship. And in fact, it could be because we are talking about partial molar quantities that really only the most active or a fairly active form of carbon is giving us the thermodynamic properties that we're attempting to measure. So that if you assume that that's the case, you can take this line, I mean this is a free energy kind of plot against temperature, you take the slope and the intercept and you have enthalpy and entropy. Turns out the entropy measured by projecting back to zero the entropy from the slope and intercept of this plot will give you about 100 kcals or 100 kilojoules and about 120 joules per mole degree for the entropy. Now that entropy number would appear to be somewhat out of line for what you would expect. 120 joules per mole above that of graphite is probably a bit excessive. It could only arise if you were perhaps talking about populating an extremely low concentration of sites with in other words, the only way I could explain that kind of number would be if you had a very large configurational entropy effect. The 100 kilojoules per mole is also probably a little high, but again, because we're putting carbon on and integrating the amount of carbon that's absorbed, and we're looking at partial molar quantities, we have to know that all of the carbon is in the same state in order to before we can really say definitively what the coverage versus free energy or coverage versus enthalpy curve would look like. So the next slide kind of summarizes this plus a lot of other data which has been defined very well, I think, from surface science experiments, particularly by Blakely for nickel. There's some work by Grabke co-workers on iron, where in these experiments where I show lines, these have been done on single crystal surfaces by segregation techniques, meaning you dissolve the carbon and then you segregate out of the surface, and you do enough of that with temperature and dissolved quantities, you can come up with some thermodynamics. Our study, on the other hand, is up in this range, fairly well above. In fact, this is more a free energy plot than it is enthalpy. We're well above the level of graphite. We're way below the enormous level of binding energy, that is the total electron energy that would be involved in taking an atom and putting it on a surface. So we're well above the graphite line, and we don't ever measure anything down this low. And I think perhaps that is the reason we see these kind of differences. We see the same thing with carbon on nickel. We're approaching it from a very high pressure regime with very high free energies. Potential free energy of formation of carbon could be quite high in these experiments. We start out with pure carbon monoxide. And so we're kind of coming from this direction down, whereas the segregation experiments are starting with free energies that are close to or slightly, in some cases, below that of graphite, and they're working their way up. So, well, what's the conclusion? The conclusion is that there can be, according to our experiments, free energies would imply that we have to have at least this kind of energetics of carbon on the surface of these ruthenium catalysts in order to be able to see the CO, CO2 kinds of ratios that we see. We could have something that's way up here, but present in very small quantities that gives us the effect that we see. But we could not really be measuring something that's down in here and still have it give us the result that we've gotten. So I think the final conclusion is that there could be very high states, reactive states or energetic states of carbon on the ruthenium, supported ruthenium. They probably are not, well, they probably are a range of possibilities depending upon the actual local coordination of the carbon atoms and or the possibility of forming carbon-carbon bonds. The next slide should show some CO. There's been, Al mentioned the production of carbon on ruthenium. I think I need to address that issue. The disproportionation reaction he referred to as, what was the word, normal disproportionation or something to that effect. It's kind of hard to say exactly how CO disproportionates on a metal surface to follow the actual bond breaking and forming steps. We always saw and always continued every time we looked at this problem to see small amounts, roughly 10 or 20% of disproportionation during a typical desorption curve, such as this curve here, where we have absorbed at 300. Now we heat up the sample and flush out the CO. We always see a certain amount of disproportionation at these intermediate temperatures. We also have carbon monoxide that's very strongly bound to the metal surface. So it's simultaneously desorbing, adsorbing, and disproportionating all at the same time. And that's how we end up with a net excess of carbon on a surface. So the next slide will show an experiment that we did some time ago and buried the paper in the Journal of Chemical Physics Letters. This is an isotope experiment where we have all four isotopes of CO. We start out with 29 and 30, and the normal isotope 28 is present in very small quantities in our original sample, and of course we have a little bit of 31. We then desorb, and we see the same on a large scale. I don't think you can see this coordinate at all, but this is 300 and this is 800 kelvins. We then accumulate all of the CO that's desorbing. It looks very much like a lot of work that's been published in the literature. But we break it down into the different isotopes, and we saw scrambling that took place around 450 kelvins, where we see the beginnings of exchange between the different types of isotopes of CO until we reach 500 Kelvin, where they're pretty much equilibrated according to the original isotopic ratios. And finally, as we go up to very high temperatures, well beyond the Fischer-Tropsch kind of temperatures, we're starting to see an influx of predominantly O16, which we presume is coming from the supported catalyst. Either from the support or in other words, when we get out to the last traces of removal of the carbon, or the CO as it originally was populated, we see almost complete removal of only isotope 16, which means it has lost part of the O18 has been dissolved somewhere into the system and is incorporated in the whole supported catalyst network. Next slide, please, shows the ratio. Now this is where we took and differentiated the exchange, the extent of exchange of the CO scrambling. We compared that with methanation. Winslow and Bell did a very nice job with this type of an experiment, published about 5 or 8 years ago, something like that, where they did a much more sophisticated set of experiments and did not find with ruthenium on silica quite this indication of correlation between this exchange and methanation rate. So it may well be something of a coincidence for our particular experiment, but it sure did look like a nice, at the time anyway, it sure did look like a nice correlation between the dissociation, if you will, if you visualize the exchange as a simple dissociation kind of mechanism and the formation of methane. This solid curve, by the way, represents hydrogen plus CO, whereas this one again was just the TPD where there was no hydrogen present. Next slide kind of summarizes the energetics, and Dr. Shostakowicz will undoubtedly, and Alex Bell will probably have a lot more to say about this kind of energetics. It may not be real visible from the back. This scale is in kilocalories. We are plotting the gases are very well known. Carbon monoxide absorption is very well known, but in general, I'd say these little lines on here are very should be really rather broad. We're trying to make the distinction for the dashed line for ruthenium and the solid line for nickel to follow the different energetics, the enthalpies, if you will, and most of these are guesses. Between adsorbed carbon, which is shown here, adsorbed carbon monoxide, as I said, was pretty well known. The dissociated carbon plus oxygen, and then some of your product gases, and just try to follow a reaction pathway, if you will, and even speculating about transition state energies that would allow the change over these different states. Now, the differences between ruthenium are that it probably does have a higher surface enthalpy of carbon with respect to some of the very tightly bound carbon states on nickel. But the biggest difference is probably the difference in the oxygen, because for nickel, the oxygen level is way down here at about minus 65 or 70 kilocalories. For the ruthenium, the oxygen level is quite high, around 40 or 35 kilocalories. And as a consequence, this could have a lot to do with the chemistry of carbon monoxide interactions on the surfaces, because it completely changes the way that you look at the traditional kind of dissociation. Iron, for example, can easily dissociate carbon monoxide, and clearly does leave both carbon and oxygen present on surfaces. Whereas something like platinum, you can't retain the oxygen very well, and you will very quickly go on to CO2, or as we are suggesting in this previous slide, reverse back to carbon monoxide. You just cannot keep it in a dissociated form. Well, I mentioned we will also, this was a talk about carbon in the form of chemisorphed carbon. The next series of slides, I think, will address the different types of carbon that are produced. Why don't we skip this slide? This was just the hydrogenation curve. This talks about, this is the curve for nickel. This is a TPE, or temperature program reaction curve, where we have put down carbon from ethylene. We then flush the system with helium to take as much of the gaseous and some absorbed hydrogen out of the system. We then program it in hydrogen, starting from room temperature, and we simply let the reactivity of the carbon that was present sort of speak for itself in terms of methane production rate. Now, if we absorb this hydrocarbon or dissociate the hydrocarbon at low temperatures, we see that we can populate fairly reactive carbon. This is starting out at 500 degree absorption, 600, and subsequently to higher and higher temperatures. And as you go to higher temperatures, you clearly deplete this reactive form of carbon, and you start to grow much less reactive forms of carbon. And of course, it's very well known that ethylene will form filament-type carbons, multiple layers of carbon, and these are pretty much all bulk quantities here. So that what is happening is you're growing a carbon overlayer, what I would call a carbonaceous overlayer. And we have tried that same experiment on platinum in the next slide. And you don't see very much, if any, of the low temperature states. We're already starting the scale of our reaction at higher temperature. But you can form fairly unreactive carbon. We believe this carbon on platinum is just an encapsulating kind of layer. And at very high temperatures, you essentially can pulverize the ethylene and end up with a very dense form of carbon that's hard for platinum to gasify and requires 800 or 900 degrees C to be able to do so. Ruthenium is somewhere in the middle, and our next slide shows, I think, a system where we've been studying for the last several years the carbon states on ruthenium. We do this as a routine analytical procedure. This represents a steam reforming experiment where we are injecting naphtha and water in a pressurized system. We're running at 25 atmospheres. And we have the capability to flush the system fairly quickly. We use a fairly large amount of catalyst. We can flush the system out and then cool it, and then program it in hydrogen and also oxygen to look at the quantities of carbon that are deposited under these conditions. And we use this as a both qualitative and a quantitative analysis of this carbon states on ruthenium. Next slide. This is the result, and probably again in the back you can't quite see the writing here. This is a ruthenium on alumina catalyst. This is just the hydrogen TPR, or the gasification of a carbon state or amount of carbon that's been deposited on this catalyst. I'm plotting methane rate in micromoles per second. The conditions were steam to carbon of 0.6 in the feed gas, the natural steam feed gas. The pressure was about 375 pounds. Our reforming temperature was around 500 degrees C. And we had, this is a clean catalyst. We have other experiments where we had put a lot of sulfur on. Our goal was to determine the effect of sulfur. We ran this catalyst for 166 hours, and this is the result. A nice bulk state of carbon that is clearly a carbonaceous overlayer. It is up to 5 weight percent of the, well, in this case probably only a few weight percent of the catalyst, and it is readily gasified by this process and identified. There's very little of what you would call a reactive form of carbon. The next slide, please. And I mentioned in the abstract that I would talk a little bit about sulfur. By increasing the amount of sulfur, you decrease the amount of this state that you can produce, and you increase an even less reactive form of carbon that can only be gasified at temperatures as high as 800 or 900 degrees C. This again is probably a very dense form of carbonaceous overlayer with a low hydrogen content, whereas this one is probably a porous carbonaceous overlayer with probably much more hydrogen content. As you add sulfur, you shift from one to the other. The next slide shows the final result of that. Even when we're programming in our hydrogen at 50 pounds per square inch, we are not able to gasify all of the carbon up to 1,000 degrees C. And we go on to the next slide and we remove a lot of that with oxygen TPD. Huge quantities of of very unreactive carbon are deposited under those conditions when we had a sulfur poison catalyst, and this allowed us to tell what the sulfur is really doing is that it's not inhibiting the formation of carbon under these conditions, but in fact it's making it extremely difficult to remove the carbon. It continues to accumulate, whereas on the clean catalyst, under the conditions of steam reforming, there is a constant removal of the carbon by the steam and hydrogen that's produced, and as a consequence, you don't have a deactivation or a coking problem, whereas with the sulfur poison ruthenium catalyst, you certainly do. I'll wrap up with this next slide, hopefully. I'll skip that one. Okay, carbon reactive states. We have chemisorbed carbon that reacts according to this TPR kind of analysis at about 480 kelvins. That's a range. Ruthenium is also forms to a lesser extent, to a lesser coverage, a chemisorbed type of carbon, which is just about as reactive. Nickel will form a bulk carbide, and you gasify it with hydrogen at about 550. Nickel will also form filament carbon, which gasifies at around 800 Kelvin. Ruthenium forms a carbon state at about this temperature, but I have never seen or done ourselves the right kind of TEM experiments to identify that as a filament state of carbon or morphology of carbon. There's also a less reactive form of carbon that you can produce on nickel at high temperatures, and amorphous films. I mean, these are just guesses as to what the morphology is. There is a shift in its reactivity. This amorphous film can also be produced at very high temperatures on ruthenium catalysts. It's difficult to gasify. But I'd say these states here, you can go from like I said, a porous, partially hydrogenated type of carbon down to a much more dense film. It's difficult for both of these catalysts to gasify, but they clearly do have that ability. Okay, the conclusions. Next slide. I think it's very, it should be gratifying to know that you can produce chemisorbed carbon that could be relevant, could be in the Fischer-Tropsch synthesis. There are indications that perhaps very energetic forms of carbon could be produced to very low levels on the surface. I would say that chemisorbed carbon, depending upon its coordination and extent of hydrogenation, could have a very large range of enthalpy. And so it's not a simple matter to either experimentally determine these thermodynamic quantities, but even to know what it is you've got when you're measuring measurements. We found in the slide that I skipped through that some of the carbon, on some occasions, you could produce something in the order of 1/100th of a monolayer carbon that's so reactive that as soon as you introduce the hydrogen, it will gasify at temperatures as low as room temperature or below zero. You don't get a lot of evidence for CO dissociation at quite low temperatures, but it certainly seems to come up. We've speculated that was due to the possibility that the surface oxygen that's produced by such dissociation on ruthenium is so reactive that it goes somewhere and possibly back to CO or away as CO2. You can form carbonaceous films over both ruthenium and nickel surfaces. These can be hydrogenated and they can be fairly porous, and they're different than you produce on platinum. And then the conclusion about the sulfur I mentioned. Thank you very much for your attention.
Any questions?
John, that carbon that comes off at about 1100 degrees Kelvin, you referred to as an amorphous carbon. Wouldn't it be quite graphitic in nature, and maybe even somewhat crystalline?
I meant more amorphous in that it probably might not even have a direct contact with the metal more of an amorphous form of carbon. It would not be, you know, you can talk to people who work with carbons, and they would say that anything you made at 1100 degrees C was definitely not graphite, because it takes much higher temperatures to produce crystalline graphite. For you and I, it's close enough to call it graphite. There's no question it would have a very low level of hydrogen content, and probably would consist of you know, pretty good rows of layers of graphitic type bonding.
I am a person that works with chars, coal chars. And in coal chars, we have aromatic clusters.
Yes.
And they may range anywhere from 5 up to 50.
Yes.
But in the chars, they tend to range on the order of 15 to 20. And so in that kind of carbon, you may have aromatic clusters on the order of 15 to 20.
That's what I'm kind of thinking about. Yeah, that sort of thing.
Yes.
Do you think that any of the carbon reductions materials might be associated with the support, and what effects of the support have you seen in your work?
Oh, I think there can be some support retention of carbon. I haven't seen, well, you can make these kinds of, some of the chemizoic states could be produced on neat, meaning unsupported metals. And I would say, you know, hazard a guess to say that a lot of the other stuff, the high temperature stuff, could really be support related, where you're putting some hydrocarbons out on the support and kicking it back off again, that sort of thing. We have not done a systematic study of that at all. But I have no doubt that you could put carbon overlayers on a support surface